Hello everyone, I'm Nicklas, and in this recorded presentation, I will introduce our work with the title Self-Supervised Policy Adaptation During Deployment. And in this work, we investigate the problem of adapting a pre-trained policy to new environments without any prior data from the target environment and without assuming access to a reward signal. So, deep reinforcement learning allows us to solve complex tasks by end-to-end policy learning. And in many cases, we can even solve tasks directly from image inputs, which is what we mostly consider in this work. But a policy learned in one environment may not always generalize to other environments, even when the differences are only perceptual. And in fact, the problem of generalization can actually be observed across a variety of environments and tasks. So how can we close this gap? Previous work addresses this problem by randomizing elements of the training environment that are also expected to change during deployment. So for example, if we expect colors to change at test time, we can also randomize colors during training. And this technique is usually referred to as domain randomization. But training on a large distribution of environments also makes the policy optimization more challenging. For example, in a sim-to-real situation, we may want to randomize many different elements, but at the same time, too much randomization is also known to reduce the sample efficiency, and it can even make the policy fail to converge. And depending on the specific application, there can also be differences that are difficult to express formally. So determining what to randomize and also how much can therefore require a lot of trial and error. To demonstrate the significance of this problem, we first train a handful of policies using the soft actor-critic algorithm and without any randomization. We then train another set of policies on the same tasks, but we now randomize colors during training. And we find that this domain randomization decreases the sample efficiency substantially. So in this project, we investigate an alternative research direction. Can we learn a policy in a single environment, deploy that policy in our target environment, and then adapt the policy during deployment itself? Now, to adapt our policy, we are faced with the following challenges. First of all, we may not have access to any data from the target environment. And second, we also cannot assume that we will have access to a reward signal, as the target environment could, for example, be a physical robot. So to address these challenges, we propose to adapt online using a self-supervised training signal, and we only use data collected during deployment. Our algorithm consists of two phases: the initial training phase in a fixed environment, and then an adaptation phase during deployment in the target environment. So first, we divide our policy network into an encoder and a policy head. During training, we then jointly optimize a self-supervised task together with reinforcement learning, with both tasks sharing the same encoder. And then during policy deployment, we cannot assume access to reward signal, and we may therefore not be able to optimize our policy using RL. But we can still optimize the self-supervised objective, and we can use the observations that we receive from the environment. During deployment, our algorithm works as follows. At each step in the new environment, we take an action, we receive an observation from the environment, then we perform some stochastic data augmentation, and then we take a gradient step with respect to the self-supervised objective, using only the observation from the current time step. And we then repeat this process at the next time step. In this work, we consider two different self-supervised tasks. First, we learn an inverse dynamics model. Given two consecutive observations, the model learns to predict which action was taken in between those two observations. And then in the second task, we adopt a rotation prediction task from the field of computer vision. In this task, we randomly rotate an observation by one of 4 different angles. And the task is then to predict which way the observation was rotated. And we cast this as a 4-way classification problem. We find that the best choice of self-supervision actually depends on the RL task. But in general, learning an inverse dynamics model is better for tasks that require more motor control, and rotation prediction is usually better for navigation tasks. To evaluate our method, we learn policies in a fixed environment, and we then evaluate the learned policies in more than 100 environments and across many different tasks. For example, we learn a policy that solves the cart pull task. In this task, the objective is to control the cart such that the pull remains balanced. During training, we jointly optimize the RL objective together with an inverse dynamics model. And we then transfer the learned policy to an environment that differs in color. And we find that a direct transfer of the policy fails to solve the task, whereas our method adapts to the new environment within a single episode of interaction. We also consider adaptation to non-stationary environments. In this example, we replace the background with a video, and we record the cumulative reward received during the episode, which is shown here on the right. Our method is able to continuously adapt to the environment and remains balanced throughout the episode. And in this task, the objective is to run forward as fast as possible. While the baselines fail to move during certain parts of the episode, our method is relatively unaffected by the changing background. And overall, we find that our method improves generalization in nearly all instances. And our method is not limited to visual changes. We also train policies for robotic manipulation. First in simulation, and then we adapt the learned policies during deployment on a physical robot. In the task shown here, the objective is for the robotic arm to push the yellow cube to the location of the red disk, and the policy takes images as input with no access to state information. In the real world, we consider three different environments. First, an environment that is similar to the simulation, but still has some subtle differences in both visuals and dynamics. Second, a discolite environment, where moving discolites distract the policy visually. And third, an environment with a tablecloth. And because of the fabric, there's a lot of friction between the table and the cube here. In all three environments, the policy receives observations from an uncalibrated camera, and we also make no real effort to match the physical properties. Here, the learned policy solves the task in simulation. A direct transfer of the policy often fails to solve the task. While our method successfully adapts to the physical robot and actually matches the success rate of the simulation, even in the presence of discolites. And we repeat this experiment for the tablecloth environment as well, and we see a similar pattern here. A direct transfer of the policy fails to solve the task, while our method succeeds in most cases. And because of the high friction, the robot actually fails to reach the goal in a single motion like in simulation, but still solves the task in a few pushes. For more information, we encourage you to check out both our paper as well as our open source implementation of our method and our benchmark available on this link.